Hi, everybody. I am going to be recording a lecture on repeated measures ANOVA, and I am going to go ahead. So it's chapter 13, and I'm going to cover repeated measures ANOVA, and then we'll cover two-way ANOVA separately. I'm going to go ahead and share my screen and pull that up. And then I'm gonna leave it just in this view rather than launching it because it interferes with Zoom a little bit. But as we talked about, ANOVA is analysis of variance. And just like with the t-test, a repeated measures ANOVA is going to be used within subjects design. So we are using a one-way ANOVA, which is going to apply when we only have one independent variable or a single factor design. It can either be a true independent variable that involved an experimental study and it was random assignment, or it can be a quasi-independent variable. And you can have the independent measures that we talked about in chapter 12 as a between subjects or between groups design. This particular chapter is going to focus on your within subject or within groups design, where you have the same people in each group being measured repeatedly, thus being called a repeated measures ANOVA. We're also going to cover in a follow-up video a two-way ANOVA, where you now expand the study beyond just one factor to two factors. And that will be the degree of complexity that we reach for this class as an introductory behavioral statistics class. But I highly encourage you to take future classes at the undergraduate level when you transfer, because it'll help better prepare you for grad school. Most careers in psychology need a graduate degree. So I would encourage you to start building those skills. Remember, learning is an iterative process. So not everything will sink in this time in this class, but I'm planting seeds. If you take a subsequent class, then those seeds are going to be watered and then they will come into fruition over time. I promise you. So be patient with yourself, okay? Okay, so when we talk about a single factor repeated measures design, we're looking at a research design that can either be with an experimental study where there's manipulation of that independent variable and you're randomly assigning people to groups, or there can be non-experimental independent variables or quasi-independent variables where the two groups are already formed and then you're just making comparisons across those groups. Remember that with ANOVA, although it can be utilized when there's only two or more groups, for the purposes of this class, we'll apply ANOVA with three or more groups. And the more conditions or levels for each factor, the added complexity involved. So keeping it at three conditions or three levels is the most basic one-way ANOVA that we will do in this class. In terms of applying our hypothesis steps testing, it's the same exact concept that we used for an independent measures ANOVA. We're going to have a null and alternate hypothesis. And the null hypothesis is that the IV does not impact the DV, so there is no treatment effect. And again, just like all the other techniques that we've utilized, typically your null and alternate hypothesis are written with population parameter notation. And so we're saying that the means for all three groups equals one another, and the alternate, they do not equal one another. So you can either express that by saying it's not the null, you can say that they don't equal one another, or you can be more specific. So if your theory or your predictions are specific and they're guided based on previous research, great, you can be specific. Otherwise, the most generic will just say where it's not the null hypothesis and that differences do exist. Similar to kind of all the structures we have looked at, the general structure conceptually for the F ratio and the formula is the same. We're looking at between groups differences or variances between the sample means divided by kind of the variance that we would expect without any treatment effect. So that's just kind of the residual leftover variance that exists. So with the repeated measures ANOVA, we actually add an extra step, because not only do we parse out these two types of variance, but then we separate out this denominator even further. So we're actually going to look at our numerator is looking at differences between treatment conditions, right? And that's just without the individual differences, just differences between treatment conditions. And then the denominator is actually looking at what are the differences without the treatment effects? So what are the residual or leftover? So we talk about those as being random unsystematic differences, or we talk about those sometimes as being error, okay? And so what we want to do is we want to break up this error, this random unsystematic differences, to kind of error variance, that residual variance that's left over. So with the numerator, we're going to continue to keep those systematic differences between treatments, and we're going to try. What we end up doing in this one is, because you have the same people in each group, the differences between the groups is purely due to the systematic differences. It has nothing to do with individual differences, and that's because you have the same people in each group, because it's a within group design. So we're controlling for those individual differences in the numerator. And the denominator, you're also, you know, those individual differences are no longer a factor, and so you have this residual or error variance left over. So in the first treatment, similar to our independent measures ANOVA, we separated out and we parsed out variance to between treatments and within treatments. Now we're going to take another extra step, and we're going to further parse out that within treatments, and we're going to look at individual differences between subjects. So how does participant 1 differ from participant 2 from participant 3? And then what's the residual error left over that is just due to potentially sampling error? You do have pretty much all of the same notation that we introduced you to in independent measures, with one exception. We're talking about now P. When we talk about P, we're talking about a person's total. So capital P represents, if Ajanette was in this, it represents my total score. So my total score from measurement 1 plus measurement 2 plus measurement 3, okay? And it helps us to look at the magnitude of the differences or the changes in my score over time. So that's pretty much, and also let's distinguish between our capital N. Before, our capital N in an independent measures represented the total number of participants, but since we have the same participants in each treatment condition in a repeated measures ANOVA or within subjects design, our capital N represents not participants, but the total number of scores. So if you have 10 participants, you have scores 1 through 10 for measurement A, then you have scores 1 through 10 for measurement B, and then scores through 1 through 10 for measurement C. So that's a total of 30 scores, even though we only have 10 participants, okay? So those are the only two differences. Other than that, all the other notation is the same. Our first step for a repeated measures ANOVA is identical to what you were exposed to in the independent measures ANOVA. We're going to calculate our sum of scores total, sum of scores between treatment, and our sum of score deviation within treatment. But then we're going to add this second stage, and this is so that we can break out those individual differences from the denominator and divide by our leftover residual error variance. And how we do that is we're going to calculate between subjects sum of score deviations, and we're going to subtract that from our within subjects sum of score deviations. And what's left over is going to be our sum of squared error. And that's what we call our residual error. So we're taking all of this error within groups error, and we're fragmenting it out in that denominator. So looking at our formulas, here's stage 1, sum of squares total. We're going to need to calculate our sum of squares within treatments and our sum of squares between treatments. And then we're also going to do in stage 2 our sum of squares between subjects. Now we're talking about individual participants, and our sum of square errors. Okay. And then here's your mean squares. Ultimately, your F formula is this. So if we work backwards, your F formula is going to be your mean square between treatments divided by your mean square error. To get mean square error, we have to take our sum of squared error divided by our degrees of freedom error. In order to get that, we're going to have to calculate our sum of squared errors, which is all part of the previous formulas. Okay. And then you also need to know your formulas for degrees of freedom change. So your degrees of freedom, you have more degrees of freedom now. You're going to have a degrees of freedom total between treatments, so between measurement A and 1. Within treatments, so within measurement A, within measurement B. You're also going to have between subjects, so between individual participants, and then your error. Okay. It's a lot, right? Just like with the other ANOVA, we've now moved on to using partial eta squared. And that partial eta squared is still telling us what percentage of variance is accounted for through our independent variable or through our treatment. Our formula pretty much stays the same conceptually, but we do have an alternative, which is it still does the same thing. So regardless of which ones you utilize, it's going to end up with the same result. And then just like with any analysis, our independent measures ANOVA, when we have 3 or more conditions, the F test itself tells us that there were significant differences between conditions, but it doesn't tell us which condition was significantly different from one another. So we know that if we have 3 conditions, there's differences between those conditions, but we need to do post hoc analyses after the fact to determine, is A different than B, is A different than C, and is B different than C. So once we have this significant F test, then we calculate our effect size and look at the magnitude of that treatment effect. And then we do our follow-up post hoc analyses to determine which of the which conditions are different from one another. So we do a post hoc analysis comparing every possible pair of conditions. And we would use a Tukey or the Scheffé is where I lean. Now, and we do it kind of in that order, where we first find out if there's significant differences. If so, we do an effect size, and then we turn around and calculate our post hoc. And we do that manually, right? If we're doing it manually, we do one step at a time. But when we enter it into SPSS, we don't do it that way. When we enter it into SPSS, we just plug it all in at the same time. And while we're in there, we just go ahead and click to give us our partial eta square, and we check the boxes to do our post hoc analyses. So all one swoop, it's there. But we don't interpret that eta squared, or we don't interpret and report our post hoc analyses unless the F test is significant. Okay, when we do report, we need to adhere to appropriate APA formatting. So that's in the literature section of each of your chapters. And so that is actually seen down here, where we're saying what technique, were there significant differences in the DV based on the IV, and then we have our statistical evidence. If it was less than 0.05 or less than 0.01, whichever alpha level you choose, you have to report your effect size. And then you're going to go on and follow up using the formula that I gave you, and you're going to now have a statement of interpretation, do your post hoc analyses, and tell me which treatment conditions are different from one another. Okay? And then, of course, you need to report the p-values for each of those post hoc analyses that are significant. Okay, So in terms of the assumptions, if you recall, are the criteria that has to be met in order to accurately and validly interpret the results of this statistical significance test. If this significance test, if we're violating these assumptions, then we can also kind of question whether it makes sense to use this technique or not, okay? And so our assumptions are consistent regardless of whether it's an independent measures or repeated measures analysis. The only difference is the homogeneity of covariance, and we'll talk about that in a second. So first of all, we have to have independent observations, which has been an assumption all along. Secondly, we have to have a normal population that we're referencing. Thirdly, we have to know that each variance within the treatment should be equivalent. And then finally, we're going to add homogeneity of covariance, suggesting that each subject in each of the treatment conditions, the treatment's consistent for each subject across conditions. So let me explain this. Let's say I was trying to see if active learning was different than passive learning. And I had 10 participants and I'm doing exams to test their knowledge. What I might want to do is first do passive learning with the first 5 and then active learning. And then I'm going to flip-flop that and I'm going to do the other 5. I'm going to start them with active learning first and then passive learning. And what I want to see is, are those between treatments variances from passive to active consistent with the between treatment variance of active to passive? So it's almost like adding another independent variable, looking at the order of the treatments, but not quite, right? And so we are looking at that covariance. What is the co-relationship between the variance for your counterbalancing, okay? And counterbalancing is an extra step that you have to do within your treatment, within treatment designs or within subjects' designs, so that you can control for order effects. Just the fact of taking the measurement the first time, you might develop skills and experience that help you do better the second time. So when you take it the second time, is it really due to the treatment, or is it possibly due to just the practice and exposure that I got the first time? So when you counterbalance and you give half A first and then B, and then the other half B first and then A, what you're doing now is you're counterbalancing to see if A did in fact help B, but if you find the same variance and the same patterns, whether they took A first or A second, then you know that it's not the order effects, it's truly the treatment effect, okay? Okay, let's talk a little bit about how repeated measures T and repeated measures ANOVA are similar. When we talk about t-test, obviously we only have 2 conditions. With ANOVA, we're going to have more conditions, but let's say you only have 2 conditions in your repeated measures ANOVA. Your results are going to be the same. If you rejected the null with the t-test, you're going to reject the null with your f-test. So f, remember, f equals t squared. So whatever your t value is, you're going to square that, and that's going to be your f value. Your degrees of freedom in your t-test, the denominator of the degrees of freedom in the f ratio. And so ultimately, it's going to result in the same conclusion. So if you reject the null, you're going to reject the null, okay? And then I think that's, I'm going to walk you through SPSS, and then we'll wrap this one up, okay? When you talk about repeated measures ANOVA, you actually have a separate column for each treatment condition. Remember, each row is a single person. So you report what their score was in condition A, then B, and then C, and then so on and so forth, right? If you have more than one level. So you're going to have a different column for each condition. The data that you actually input is the dependent variable scores. So make sure your labels and your headings are appropriate. And then you're going to follow the instructions necessary when you're running the data analysis. And so here's a learning check for you. And I'll actually do this with you in the lab. And you can do it either, you can plug in the data that's given to apply the formulas manually, but we'll run it in SPSS in our lab. You should know that SPSS, the basic package, does not run a repeated measures ANOVA. So I'm providing you the instructions so you'll have that as a reference. I will not have you actually run a repeated measures ANOVA per se on your own. I will demonstrate and teach you how to do it because my SPSS does, and I want you to be familiar with that. And I want you to keep that as part of your course archives for reference in future classes. But you should know that, that in terms of our exam and testing, you'll have to interpret the repeated measures ANOVA accurately. You'll have to recognize when to use the repeated measures ANOVA, but I won't actually have you run one in SPSS, okay? And then I'm gonna wrap up here and we're gonna come back and have a follow-up video looking at a two-weight ANOVA or a two-factor ANOVA. Okay, take care. I'll see you in lab.